I will take over with the details about the project and what we did for the ozone at the Bottrop pilot plant. So I will guide you step by step through the different phases of the project, starting from step one, which was grounded on the batch tests we performed together with the laboratory in Germany, the Utah lab. And here we perform the batch test. As you can see here in this figure, we inject ozone in a controlled way into a water sample of the water matrix sampled at Bottrop at the effluent. And in these figures, you can see the results for a high ozone dose that we tested was 0.6 grams of ozone per grams of DOC. In particular, if we look at on the left graph, you can see the residual of ozone in water in time. So there's the decay of ozone. And we calibrated our AMOZONE model on these lab data. So we calibrate the ozone residuals and also the bromate formation that we could see building up in time as a byproduct of ozonation. Starting from this point, we could calibrate the model accurately on the water matrix of Bottrop effluent, and we could simulate in the second phase with the process model a preliminary. We could do a preliminary study focusing first on the residual of ozone at the effluent in order to assess whether the volume estimated at first was enough to grant a low residual in the effluent, and whether there could be the possibility of reducing the volume and as well the costs related to the construction of the reactor. So in this study, we could see that actually the initial volume was resulting in very low residuals, and there was room to reduce the volume further with still granting low residuals in the effluent. At the same time, we wanted to test different specific ozone doses and different DOC levels to see the bromate formation that could be experienced at the Bottrop once the reactor would be built. And as you can see on the right, the bromate formation at the lower ozone dose of 0.4 was below 1 microgram per liter at any DOC level tested, while with the higher ozone dose, the bromate formation was below 4 microgram per liter. So still a feasible ozone dose in order to stay below the limit of 10 microgram per liter that was present for the Bottrop effluent. So in this feasibility study, in step 2, we could get the first insights. And then once we move to step 3, so with the CFD-AMOZONE model, we coupled the kinetic modeling of AMOZONE that was previously calibrated on the batch test. We coupled it with the CFD in order to see in detail in the space in the reactor how the different concentrations of ozone and bromide and bromate and micropollutant removal would look like. So what you can see here in this image is the side view of the pilot reactor at Bottrop, the initial design. And here we had bromide in the influent of 350 microgram per liter. Then there was a countercurrent configuration with the 2 injection chamber, the first one and the third one. And with an ozone dose of 0.4, we got an effluent bromate of 3.4 microgram per liter. We could see with this CFD analysis that the average removal of the micropollutants of the current list was around 70%. So it was below the 80% target. And we could also see that actually after the 4th chamber, there was nothing happening. So bromate was already formed. Micropollutants removal was already reached as in the effluent. And also the ozone residuals were almost zero already after the 4th chamber. So we could see that there was actually room for optimization. And in the subsequent step 4, we actually tested more scenarios, testing different designs. This one is the last one we chose, so the one performing better. And as you can see, we have reduced the number of chambers from 8 to 6, and we have increased the number of injection chambers. So we have diffusers in all the 4 forced chambers. In this way, we could actually reduce the local ozone concentrations compared to the initial design, thanks to the fact that there are more diffusers that can deliver the same gas flow. So the ozone concentration is actually lower. And then in this way, with diffusers in 4 continuous chambers, the EGLV can also try to operate the reactor in different ways. So the counter current, which is something typically used in the past for many years. This is the design typically in place from previous reactors, where the flow of water is in a counter current direction compared to the gas flow. So the water flows down in the first chamber while the air flows towards the top. And this is the counter current, in which only the diffusers in chamber 1 and chamber 3 are active. While there are also other ways we can operate the reactor, which is the co-current design, where the water and the gas flow in the same direction. So only diffusers in the second and fourth chambers are active. And then we also modeled and tested the reactor in the hybrid configuration, where we have the diffusers operating in all the 4 chambers. So we actually have at the same time the counter current and co-current operation. You can see here the results for the ozone gas concentration. So you see in the counter current configuration, we have ozone only injected in the first and third chamber, while in co-current second and fourth, and hybrid, we have the ozone in all the 4 chambers. What we can observe is the difference in the gas plume. If we look at the counter current, the gas is more pushed towards the bottom, while in the co-current configuration, due to the same flow direction of water and gas, the ozone is more spread along the height of the reactor. Similarly, we can observe the same thing for the ozone concentration in the water. So different ozone with the counter current and the co-current, we have the same behavior with the ozone more pushed towards the bottom in the counter current configuration, while in the co-current is more spread across the height of the reactor. And this actually results in a different impact on bromate formation, because due to this more concentration of ozone in the counter current situation, we have also higher bromate formation due to these higher local concentrations. That results in the end in 1.4 microgram per liter of bromate, which is lower with respect to the initial configuration of the reactor, much lower. It was initially around 3 microgram per liter. And this is thanks to the more diffusers we have put in place and the different design used. But we can also actually improve more the performance in terms of bromate formation using co-current or hybrid configuration. Thanks to this major spread of ozone concentration in the co-current, we are below the counter current emission of bromate, and we reach 1.1 microgram per liter. But then with the hybrid configuration, by spreading the gas flow between the 4 chambers, we have even lower ozone concentrations, and we reach 0.8 microgram per liter of bromate in the effluent, which is very well below the threshold of 10 microgram per liter. Then we also focused on the performance of the reactor in terms of micropollutant removal. Here you see the example of two micropollutants, metoprolol and clarithromycin. They are two very different micropollutants responding differently to ozonation, so that's why we chose those. But for both of them, you can see that with respect to the initial design, we could detect an increase in performance, so an increase in removal of almost 5% with the new design, with similar efficiency for the different operations. So countercurrent, co-current, and hybrid actually gave a similar efficiency. And also in terms of bromate formation, if we look at the hybrid configuration, we actually could reach a 75% reduction of bromate, which was very significant due to the restriction and the high levels of bromide in the influent. And also thanks to what we could observe in terms of ozone residuals, but also if we look at the micropollutant removal and bromate formation, we see after the fourth chamber, the results are quite similar and stays constant in the subsequent chambers. So we actually could indicate still a large improvement in reducing the footprint and at the same time lowering the costs. So it's actually feasible to reduce the footprint thanks to this analysis. The fact that the water matrix is actually eating very fast the ozone, the residuals in the end are quite low already after injection. And as a last step in this project, we actually wanted to move from the CFD that in which we could test a specific fixed condition, so with a specific level of water quality in terms of DOC, ammonia, nitrite. We wanted to actually see what happens during the real operation of the plant in the future. We know the influent the secondary effluent is not with the steady state water quality, but we might experience peaks in DOC, ammonia, nitrite that are actually very well affecting then the results in terms of bromate and micropollutant removal. And also there might be spikes in bromide at the plant, as Torsten anticipated. So we wanted to simulate these more than 70 days of dynamic influent. And here you can see the results. We performed at different ozone doses. So we wanted to see if we then are going for a higher ozone dose, what happens in bromate at a different water quality. There might be the risk maybe in reaching the threshold of 10 or also having higher concentrations. But the answer was no. Even at the higher ozone dose, the bromate threshold of 10 was actually never reached. And at the same time, also, you can see in the graph at the bottom, we tested different ozone doses with different bromide in the inlet. And here we actually could assess a good range for EGLV to operate the plant that was between 0.45 and 0.65 grams of ozone per grams of DOC, which allows at the same time to stay below 10 microgram per liter of bromate, but also to reach the target of the 80% removal of micropollutants. And on the right, you can see the two series are actually representing the average for the micropollutants of the CAR list, but also we wanted to assess as well the removal, the average removal for the 12 micropollutants of the European Water Directive. So we were able to actually also report and suggest an optimal dose range. And this, at the same time, with the dynamic process model, we could actually prepare a kind of digital twin that could be that can be used by EGLV during the piloting phase, during the operation of the pilot.